What? So suddenly, I'll put it this way. So suddenly, about 1/3 of the class, just went from F to almost B's. But that's the way that I decide to grade and the way I want to ask questions. All right. So let's go ahead and do it, this way. Let's go ahead and deal with the practice exam first, and then we'll go back to the homework assignment. I'm not going to add predicate calculus anymore. There's not enough time to do it. So today is going to be the practice test because it's 1 week from the actual final. So I want to do it today. Yep, go ahead. It is cumulative in the sense that the material that you understood earlier, you should still understand it, because it will still be reliance on set theory, set operations, and so on. And I think the mic is still picking me up when I'm walking over there. So that's kind of cool. So it is cumulative from that sense. Um, Am I going to ask questions about CNF? Well, maybe, but then maybe not. So, but it'll be heavily focusing on the graph stuff that we have been talking since the second exam. Okay. All right. So I'm going to show you what I did last semester. So last semester, let's see, this is a 440. It is open book and open notes, and you can bring a scientific calculator with you. So if you feel better with a scientific calculator, bring it with you. It's not a problem, but any other electronics is not going to be permitted. This has been up since the beginning of the semester already. This is the actual test and solution from the previous semester. So in the previous semester, I asked about the Dijkstra's algorithm. I may ask about the A-star algorithm for this semester, so you need to understand the A-star algorithm as well as the Dijkstra's algorithm. But I will give you the algorithm, at the beginning of the test. So if I ask about the A-star algorithm, I'll give you that. So there's no need to print the A-star algorithm to bring it with you, even though, okay, I might give you something that is kind of concise. I would still recommend you to bring whatever you think will help you, okay? And most of the time, it is not the code that is the issue, it is the interpretation of the code. What is this line doing? Why is there a loop over here? What is this condition testing? What does it mean if I go into the then branch of the conditional statement? So those tend to be the more important part compared to the actual pseudocode. The actual pseudocode is not that difficult. But in order to follow it or to analyze it, understanding what each part is doing is important. Okay? And then the trace of that is done at the very end. Okay, so you guys already have access to this PDF. You can just print it out. And this is the trace that I did last year. It should look very familiar with you because your homework assignment is something like this, except much shorter because we have a much simpler graph for the homework assignment. So NC is no change, in this notation. So if you zoom in a little bit, and you see NC, that means no change. So I make it very clear that even though I'm supposed to take out potentially an edge out of the set, there's nothing to take out, and that's why I use NC to denote that there's no change. So that's one of the questions. It's basically just a trace type of thing. So for the most part, it is a little bit time consuming, but you also have to fully understand the algorithm itself so that I can track down, so I can look at your trace and see whether you fully understand how it works or not. So are there any questions about that kind of question? Yep. So in the previous year, that's what I did. Okay, so one of the pages at the end here is somewhat pre-formatted. This is supplied by me to the entire class. So there's an answer sheet that is kind of like a table. It's pre-formatted with a column for V, a column for WV, W is the incoming neighbor, a column for Q, column for E prime, and all the L values. So if this is for A star algorithm, obviously the labels will be different, but it will be supplied to you. So this way, you just have to fill it in, and you don't have to spend time to make your own table. Yep. I may not. I was looking for that, but I cannot seem to find it. So you can ask your, if you have a younger sibling, just give the younger sibling a whiteout. Yep. Or you can also have it done digitally too. It's like just erase it from the bitmap. All right. So the more tricky questions is not the trace. The more tricky questions are something like question number 2. So let's check out number 2. Okay, I'm going to zoom in a little bit. There we go. So number 2 is asking, consider a directed graph, blah, 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 such that there's at least one path from each vertex to at least one destination vertex. We know that there's at least one destination vertex. In other words, it's not a graph. There is solution to this graph. Okay, this means after running Dijkstra's algorithm. Okay, so I'm gonna show you the text here because it's a little bit out of here. There we go. Every single vertex of V has a L value that is not infinity. Okay. Now consider the output of Dijkstra's algorithm, which is G prime equals to V E prime. Comment on the comparison between the cardinality of V versus E prime, and state what we know for sure and explain why you think so. In other words, I want you to compare the cardinality of V versus the cardinality of E prime. How do they relate? Now, when I ask about how things relate, in a sense, because these two are numbers, right? We are not comparing the elements of the sets. We are comparing the cardinality, and those are just natural numbers. So when I ask about what is the relationship between two natural numbers, typically it is greater than, equal to, less than, not equal to, that sort of thing. Okay. So what do you think? Okay. The answer is there, okay, but I doubt you guys can read my poor penmanship that quickly. Yep.
It's saying that the list of vertices you give us must always be greater than the subset of the edges, because there will always be more vertices than edges.
By how many?
At least one.
By at least one. Okay, so you have to read the question carefully because I want the answer to be more as specific as possible.
My answer wouldn't be good enough.
What was your question again?
So
And what was your answer again?
my answer was the set of all vertices V will always be greater than E prime, because there will always be at least one greater vertex than edges.
Okay, so it is not incorrect, but if there's enough information in the question to make it equal to, then equal to is considered a better answer than less than or equal to.
But I said greater than.
Huh?
I said greater than.
Greater than?
Yeah, V is greater than E prime because there's always more vertices than edges.
Mm-hmm. Yep.
I think it's because it is a directed graph. It would be otherwise, like non-directed graph, and have more edges.
Why would it matter?
Because you only have one edge you need to connect with each vertex. But if you need two vertices, it really shows. That's just the start.
It should not matter because of the way we construct the graph. Because a non-directed graph can be considered as a directed graph, but you have edges going in both directions, and they both will have the same equal weight in this case. So the solution graph would still have the same properties. That wouldn't change that particular property of the solution graph. Okay. All right, so let's see if I can, answer this one, better here. So there's at least one path from each vertex to at least one of the destinations. Okay, so that's the first given. We know there is at least one destination vertex. So this means after running Dijkstra's algorithm, every single vertex will have an L value that is non-zero. Okay, so you have to think about this in your head, with different types of scenarios. Okay, so the first scenario. Okay, let me see if my tablet is cooperative now because I didn't charge it over the weekend and it was definitely having a. Yep, it's still charging at 1% right now. So I may not be able to use my tablet today. Um, well, in that case, we can use the whiteboard once I find a marker. Oh, got it. Okay. So you think of a few scenarios. Okay, so you think of a scenario where you have, okay, let's say six vertices. Okay, and the solution graph looks like this. Okay, so you have six vertices, five edges. The number of vertices is greater than the number of vertices. Okay, that's one. But you can also have a scenario like this. Same, we have six vertices, except these three are destination vertices and these three are non-destination vertices. It can work out so that you have a solution like that. So in this case, we have only three edges to connect, each of the non-destination vertex to a destination. Yep.
Um, will the destination vertex or vertices not point to other destinations?
If it does point to, it would not. That edge is not going to be a part of E prime. Yep. So that means, under these assumptions, um, the output of the answer that I present here is correct. It is just greater than the cardinality of V is greater than the cardinality of E prime. Okay, so I'm gonna kind of put you on my side so that you guys can say, I'll let you guys think about, how do we change the question so that V, could the cardinality of V is exactly E prime plus 1 or the cardinality of E prime plus 1. So what condition do we change here so that we can just lock it down and say it's not just greater than, it is exactly the cardinality of E prime plus 1. How do we change it? In other words, how do we coerce the graph so that the solution is going to look like this? What condition do we have to impose to make it happen like that? Yep.
Would it be that there has to be one destination?
Yep, that's it. So the only condition that you need to change to make that happen, I will clarify what that is instead of saying there's at least one destination vertex, you say there's exactly one destination vertex. That constraint will make the graph be a single tree, and because it is a single tree and every single vertex connects to the root of the tree, the number of edges will be the number of vertices minus 1 exactly. It is not just going to be less than, it is going to be exactly the cardinality of E prime minus 1.
So if you said that we
Plus 1, sorry.
so if you said that we can't just simply do like the same answer with V is greater than cardinality of V is greater than cardinality of E prime. We have to say that there is exactly one less edge, one less
Mm-hmm.
value
So,
in E prime.
so I'm just going to say it like this. The cardinality of V is going to be the cardinality of E prime plus 1 if we add the constraint that there is one and only one destination vertex. So instead of saying there's at least one vertex, if I say there's exactly one vertex, then the equality is going to hold. Yep.
And the vertices go through, if there's a shorter path through other vertices to get to the destination, or does it have to be a clear path only from that vertex to the destination?
Say that one more time, please.
Um, do the vertices have to have a direct connection to the destination,
Nope.
or can they go
Nope.
through?
Doesn't have to.
I
So
mean,
if
yeah, it would still.
so, okay. So let's say we are doing. Yeah, so we can degenerate this graph to be something like this: 1, 2, 3, 4, 5, 6. Okay, so let's say this is the solution graph. This is the only destination, right? So we still only have only 5 edges between the 6 vertices, and that's because it has to be a tree, and because there's only one single destination vertex. That means it has to be exactly a single tree. Yep. Okay, now the question is also asking why, okay, not just what it is, but also why. So the why part has to do with the algorithm itself. Every time we add an edge to E prime, what is the constraint of adding the one edge to E prime? It is in the algorithm itself. We first remove all the other vertices from a particular vertex to other vertices before we add a vertex from that vertex to another vertex. So that is the constraint. That is why the number of edges is going to be less than less than the number of vertices.
One more time.
Okay. So when you look at the algorithm, and I'm going to magnify it here a little bit. So when you look at the algorithm, um, this part here, for each WU in E prime, do the subtraction. That removes every single vertex that starts from W before we add WV back into E prime. Okay? So this guarantees that there's only up to one edge going from each vertex to another vertex. Doesn't matter which other vertex we're going to. Okay? There's only outgoing, up to one outgoing vertex from each vertex in the solution graph. Okay? But why is it less than that? Because the destination vertex is not going to have an edge coming out of it. Is that okay? So we are relating our observation back to the algorithm itself, and then we are just using words to explain it. So that means, when you're explaining that, I can take it, just like, these verbal answers. Doesn't have to be for all there exists, that sort of thing. Just verbally arguing is fine. But you have to point out why that is the case. The second part is to comment on whether E prime can be seen as a function. In other words, can I look at E prime as a function that has V as its domain and V as its codomain as well? Okay, so what makes a mapping a function? What makes a set of two tuples a function? When we know what the domain is and we know what the codomain is.
Every value in the domain is mapped to.
Every element in the domain is mapped to one and only one element in the codomain. Okay, very good. So when you look at E prime, does it satisfy that requirement? It comes pretty close, except not every element in the domain has an entry in E prime. Which one is guaranteed not to have an entry in E prime? The destination, exactly. So that's why it does not meet the requirement to be a function. So the explanation is just like that. Now, if I ask you, how can we make it so that it becomes a function? If I let you change the domain and the codomain, how would you change one of those two so that it does become a function?
Exclude the destination vertices from the domain.
Yep, that's it. Did you guys hear the answer? You exclude the destination vertices from the domain because those are the ones that is lacking a mapping to the codomain. But once you exclude them, then it's okay because now your new domain is V but minus a set of all the destinations. So that it will be okay again. Okay, very good. Yep.
How do you actually write it to explain that as a function? Because you say E prime maps to V minus one or something like that from the domain.
Okay, so you would first have to explain why E prime, why V itself as a domain is not going to work. Because the destinations, if there are multiple destinations, then the destinations, each destination as an element, has no mapping to the codomain. That is why it is not a function. So in order to turn E prime into a function, one way to do it is to remove all the destination vertices from V as the domain, so that now you have all the non-destination vertices represented as part of the domain, and that's going to be okay because because as long as the other requirements of this question is met, which means every single vertex is connected to at least one destination vertex, then there will still be one outgoing edge for each vertex. So that's why it will still be a function in that case. So the answer is just what I said. But no, in the exam, I cannot take audio answers. You cannot just talk to your phone and then send it an audio file and go like that's my answer. Maybe one of these days we can do it kind of like that but not at this point. Hmm? I can see if cisp440 is offered online, that can potentially be a way for you guys to answer questions. And I'm pretty sure 440 is offered online at least one of our sister campuses. I think at CRC, is this class offered on, huh?
Not this semester.
Not this semester, but when it is offered, it is online, I think. Okay, question number 3. Question number 3 is asking, consider a directed graph. So this time, once again, we have directed graph. Each edge has to go from one vertex to another vertex that is fully connected by edges. In other words, there are edges connecting every vertex to every other vertices. So it doesn't connect back to itself, but it does connect to everybody else. And I use the mathematical symbol to define it. For all V and W in V, if V does not equal to W, that implies VW as an edge exists in VE. Okay, so that's just another way to spell the same thing that I used the sentence to describe. As an abbreviation, because the N and the M's will be referred to a lot, let N be the cardinality of V, the number of vertices, and then M is the cardinality of E. So work out the following cases and draw graphs for each case. So if N equals to 0, M equals to what? Okay, so this part here is what I filled in. That's part of the answer, as well as the actual graphs. So when we have a single vertex, okay, when we have no vertex, there's nothing to draw. So that's an easy graph, right? It's just empty. When we have one single vertex, okay, let me get back up a little bit. When there are no vertices, do we have edges? Nope. Okay, so when N is 0, M is also going to be 0. Okay. When we have a single vertex as a graph, and we do not have vertex edges to go back to itself, do we have edges? Nope. Okay, so when N equals to 1, M also equals to 0. Is that okay? When N equals 2, we have 2 vertices, and the graph is fully connected, which means every vertex is connected to every other vertex using an edge. Then we have 2 vertices, A to B, and then B back to A. Yep.
That's specifically because it's directed, right?
It is because it's directed. If it's not directed, it will be divided by 2. Yep. And then we have N equals to 3. So we look at the triangle thing. We have vertices A, B, C, and they are fully connected. So A connects to B, A connects to C, B connects to A, B connects to C, and C connects to A, C connects to B. So we have 6 edges. Is that okay? And then the last one that I want you to work out is N equals 4. And this is the one that got some people last year, is they drew the usual one, but they forgot about the ones that go across to the other side. But the idea is the same. So do you guys see a pattern here? Do you see how the graph for 3 vertices is actually a part of the graph of the 4 vertices? Do you see how what additional edges are added when we add one more vertex D to the graph that already had vertices A, B, and C.
One less than previous.
Yeah, here's a new guy. Okay, we all connect to this new guy. And that new guy also connects back to everybody who's already there. Okay? So this is the first part of the question. It's just to work it out. Just like kind of the proof by induction question where, I asked you guys specifically about what is f of 0, f of 1, f of 2, f of 3. Almost the entire class got perfect score for that sub part of the question, except, some people told me that 2 plus 3, 1 plus 2 plus 3 is 5.
How much
Yep.
mark them off for that?
I marked off 0.2 out of 4 points. So it wasn't bad. It was just going like, I need to make a differentiation even though it is small. Question? Yes.
So is it would the formula be with the addition of each additional vertex,
Uh-huh.
the amount of edges, if they are directed and they are back and forth, would be whatever the previous amount was
Plus.
times 2 of the previous number of vertices.
Yes, that is correct. So the new m, okay, so when we consider n equals to 5, the new m is going to be the m for the case when n equals to 4 plus 2 times the previous m, so times plus 4 times 2 times 4. Because we have vertices from all the 4 old vertices to the new vertex, and then we also have, we also have edges, okay? So we have edges going from the old 4 vertices to the new vertex, but we also have new edges to go from the new vertex back to the old 4 vertices. So that's good observation. So that's why in here, you guys know this term already, it appears. Meaning that, we observe a pattern, okay? So it appears that m equals to n times n minus 1 in general. So you can check it out. I mean, when n equals to 4, 4 times 4 minus 1 is in fact 12, okay? You back up one more case, okay? When n equals to 3, 3 times 3 minus 1 is 6. So it seems to work out, okay? So there's a pattern to it. But this is a proposed theorem. The theorem is only proposed and go like m equals to n times n minus 1. It seems to fit every single individual case that we have worked out. But is it a theorem? That's a whole different question, right? So use proof by induction to show that m equals to n times n minus 1 is correct for every natural number n. Okay, so n starts with 0, then becomes 1, 2, 3, and so on. Be sure to show all steps of the proof. So in proof by induction, there are very distinct items that you have to show me in order to get partial credit for those things. The first one is, what is your base case? Okay, so your base case has to start with a particular number. N equal to 0 would be a very good natural place to start because that's the smallest natural number. So in that case, you have to show me that, oh, look at that graph here. Okay, that graph with no vertices, that has no edges. Okay, so 0 on one side, right? And then you have to say, oh, on the other side, we have 0 times 0 minus 1, which is also 0. So the theorem is true when n equals to 0. That's your base case. Very good. The second one is going to be the induction step. The induction step itself has 2 steps as well. The first step is to restate your assumption, your induction assumption. You have to basically say, we assume the theorem is true when n equals to k. So that, the m value for n equals to k is going to be k times k minus 1. You have to state it clearly because that's going to be used in the theorem proving itself. And then the second step is the actual induction step that makes use of the assumption. And that part is basically just algebra. And then when it all works out, then the final answer has the same form as what we try to prove. So is that okay? All right. But you can see how I'm kind of twisting, graph stuff to fit things that we already understand, which is, in this case, is proof by induction. So that means it is not exclusively stuff that we have talked about since the second exam, you still have to understand what is proof by induction. The concept of set is definitely important because the algorithms are all based on set notations and so on. Do we have any questions about number 3? This is 3 out of 5. Is that okay? All right. So 4 out of 5 is asking, consider a directed graph G that is fully connected by edges. Okay, so kind of the same thing that we have in the previous question. Okay, same description for all VW in uppercase V. If V does not equal to W, then that edge VW is going to be in E. As an abbreviation, blah, 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 same thing, same abbreviation. A path P can be defined as a tuple of vertices that satisfy the following requirement. So basically, a path is a sequence of vertices where every single vertex is connected to the next vertex in the tuple by an edge. But there's no repetition of edges and no repetition of vertices. Is that okay? Is that concept fine or not? All right, okay. So the rest of this is really just saying, basically defining what is a path. From the notation perspective, a path is a tuple of vertices. That means ABC is representing a path of 3 vertices and 2 edges. AB is the first edge, BC is the second edge, okay? Let n equals to, okay, this is a repetition, okay? Let n equals to the cardinality of V is already stated here. Let K be the number of edges in a path to a particular vertex W, which is an element of V. So it's just some other vertex out there. What is the number of unique paths that end with W that has K edges? To help answer this question, and also as a means to get partial credit, consider a case where the number of vertices is 4. In the following space, draw such a directed graph and label the vertices from A to D. So same graph that we have seen before, but you can now use this as an example to try to answer the question. So now enumerate all unique paths of 2 edges to vertex B. In other words, I want to end up at vertex B, but I only want to consider paths that has a length of 2 edges. Is that okay? So how many paths, how many unique paths are there of a length of 2 edges? That's what the question is asking. So you start with B, okay? So you look at B here, and you go like, how many times can I go back 2 steps without repetition of edges or vertices? Okay, so you have to go, the first one can go to A, can go to B, can also go to D, right? It's a fully connected graph, so I know that there are edges to go back to every other vertex from B. Okay, so then the second question is, from the other vertex, how many other vertices can I make? Well, you only have 2 left because we cannot repeat vertices. The end vertex takes up 1 possibility, right? The 3 vertices as the first hop takes up another choice. So from one of these 3, A, B, or D, A, C, or D, you only got 2 choices left. So there are 6 possible ways, and this is the enumeration of those 6. Do you see this as resembling something that is also in the second exam? The combination permutation thing? This is a permutation. So in this one, this is the first part. The first part is really just to kind of make you do something with a very concrete case to understand what the question is really about. And then the second one is to say, in general, okay, so we are now not considering a fully connected graph with only 4 vertices. How many unique paths of K edges end at a particular vertex? And explain your answer. So the answer is permutation. So it's the permutation of choosing K, which is the number of edges of the path, from the cardinality of V minus 1. Yep.
So my thought process wasn't using permutation, but using Dijkstra's algorithm, to where we start with D, we explore, and we want two edges, so we want to go out to each of the algorithms instead of just
Okay.
one. Would explain that in there to where I go to that, I visit each destination once.
Dijkstra's algorithm would not be applicable here because if you have a
So I have to
graph,
update it right to the
huh?
small. So I have to update to the smallest path. Is what you're saying.
Because it okay. So if you think about it, from Dijkstra's algorithm perspective, this is B, okay, and you got three vertices, right? So you got A, C, and D. So the first hop is already looking like this,
Yeah.
right?
Yeah.
But in order to have a second hop, what is it going to look like? Oh, how can we go from how can we get to A? Okay, I cannot B cannot go back to A, okay, because that would be a loop. So C can go to A, D can go to A, but that cannot be the solution of Dijkstra's algorithm. Why can't this graph not be the solution of Dijkstra's algorithm?
Is it because there's more than one edge coming out of a vertex?
For certain vertices, such as C and D, there are two outgoing vertices, which is impossible with Dijkstra's algorithm.
So it always has to be less edges than vertices.
Exactly. Yeah. Yep. So that means Dijkstra's algorithm doesn't have anything to do with this question.
But the thought process would that be fine? Because like I said, I would still be going. I understand that wouldn't be the algorithm, but I would still be going out, exploring each unique combination with that vertex once to get to until I get the two edges and then stop there.
So the idea is the first vertex is already chosen,
Yeah.
so it cannot be considered as an option for the first hop.
Correct.
Whatever you choose for your first hop for a particular path cannot be considered as the second hop, as the vertex of the second hop. So the second hop now has bar v bar minus 2 choices. And then the further you go, the fewer choices you have because you cannot have repetitions. But we already know the graph itself is fully connected, which means if you need to have this to connect from one vertex to another vertex, there is an edge to connect it. The question is, is that path, is that walk still a path of no repetitions? So the part of making this a path without repetition of vertices is basically saying it's screaming at you without replacement. So that's how this problem relates back to the discussion of permutations and combinations. All right. So question number 5. Use proof by contradiction. So once again, I'm using graph, but it is relating back to techniques of proving here. Use proof by contradiction to show that the solution graph G prime equals to VE prime of a directed graph G equals to VE from the execution of Dijkstra's algorithm cannot contain a loop. Okay, so if you just read up to this part here, you already know how to set up the proof. The first part is to negate the theorem. To negate the theorem is to say that, yep, I think I can find a particular graph such that the solution can contain a loop. Is that okay? So now we continue to read the question here. In short, a loop consists of vertices and edges where a vertex can get back to itself traversing edges of the graph. Is that clear what I'm talking about, what a loop is? A graph that contains a loop means you can follow edges and then get back to where you start off in the first place. Okay? You may want to focus the argument on the part of the algorithm that adds an edge to E prime and argue why that step cannot complete a loop. Yep.
Does that mean you add the start vertex as the destination as well? Something like that?
Not necessarily. I'm just saying that how come I cannot have a loop inside the solution graph of Dijkstra's algorithm?
Yeah, but I was thinking to negate that, to say that there is a loop
It doesn't say that it has to involve the start vertex, nor the end vertex. Okay, using the following space, use for this proof, show all steps start with the theorem being proven and all the steps of proof by contradiction. So the theorem is this part, which is G prime equals to V E prime cannot contain a loop. That is the theorem itself. So the negation of the theorem, I put a little logical negation here, is that graph contains a loop, at least one. That's the negation. Okay, so the negation of containing none is not to contain one, it is to say contain at least one. Okay. So now we have to say why that is not possible. So if you read this part here, if G prime equals to V E prime contains a loop, it implies at least one execution of line 15. Okay, if you refer back to the algorithm, that's the one part that adds an edge into E prime, completes a loop. Does that make sense? Because every single edge of E prime is added by line 15. So, so all those steps on line 15 can be adding edges, kind of like, into the graph, but one particular step is going to complete a loop. Is that making any sense? More or less? Okay. So this means that a path from y to x, okay, so let us assume the addition of the edge xy, x being the start vertex and y being the end vertex of an edge, completes a loop. That means there's a path from y to x already in E prime. Is that making any sense? Okay, so if you draw a picture, you will see what I mean by that. So let's say, by adding this edge, I'm completing a loop. Okay, so the loop looks like this, right? So before I add the edge xy, there's already a path from y back to x. Is that making any sense? Okay, so let's see how that can lead us. Because the distance of edges is greater than 0, we know L of y is greater than L of x. Okay, L of y, which is from here to a destination, is greater than from x to the same destination. Does that make sense? Okay. Because if that is not true, we wouldn't be in that part of the conditional statement. Is that okay? Because in order to get to line 15, okay, let me scroll back up to the algorithm. In order to get to line 15, what is the condition that has to be true to go back to line 15? Line 15 is right here, and it is inside a conditional statement. It's inside the conditional statement that starts on line 11. Okay? So the condition of line 11 has to be true in order for me to add that final edge that completes a loop. But what is that condition saying? The condition is saying, L of, let's see here. So V is y in this case, and W is x. So it's saying L of y, okay, if you refer back to the red graph here, L of y plus the distance from x to y has to be less than L of x. But that's a contradiction. That cannot be the case. Do you see why that is now a contradiction? Right. Yep. So that's why we have a contradiction, and the contradiction concludes the proof itself. So it's the analysis of the algorithm itself to basically say that is not possible, because in order for me to end up here, this condition has to be true. But if that condition is true and after this action, then the other condition cannot be true anymore. So now we have the conflicting logic, or there's a contradiction, and that concludes the proof of proof by contradiction. Is that okay? But since you already know that I have beaten the Dijkstra's algorithm to a pulp now, um, your exam is going to be on A star. Okay, so how do you study for the final exam if you already know that your exam is going to be based on A star algorithm?
How to prove by contradiction.
There'll be some of that stuff, okay, but what is the first step to prepare for the final exam?
Training notes.
Hmm?
Panic.
Okay, okay, so let me ask you a follow up question. What happens after the panicking? Panic some more.
Procrastinate.
Procrastinate. Okay. Avoidance, right? Yeah. Okay. So,
Procrastinate, then panic.
so the first thing is to read the algorithm and make sure you understand what each step means. Okay. So start with the symbols. Okay. What is function g? What is function f? And what is function h? Okay. Tell me. I'm studying with you now. Hmm? H is the heuristics, and H needs two arguments, right? So technically speaking, you need to give it two vertices, and it is giving you an underestimate of the length of the shortest path from the first to the second vertex. Huh? Zero is a valid, heuristic, yes, but zero is not the only heuristic function. Yep. But in your mind, if you want to turn it to zero, that works in certain cases. Okay. Yeah, if you turn H heuristic into a zero, you will see that the pattern of how you explore things with A star will start to resemble Dijkstra's algorithm, except one starts with an destination vertex, the other one starts with a start vertex, but they work about the same way because you're just being greedy and choose whichever one has the shortest path from a start vertex in this case, and you just say that's the most promising one because you have no actual estimate of how much it will cost, how much more it's going to cost from any vertex to the destination. So that's correct. Okay. So start with those symbols. So we know what h is. What is g as a function? G of a vertex is telling you what?
The graph.
Not no lowercase g.
Oh, it's the shortest distance from this vertex you're considering from the start.
Correct. So g of v for some vertex v is the length of the known shortest path from the start vertex to vertex v. Now, I said known because it is updated as we go in the algorithm. So it's only up to this point. This is the length of the shortest path that I currently know from the start vertex to that specific vertex. Okay, so now, yeah, go ahead.
Quick question on the homework you gave us. Can we like modify that to be the A-star algorithm essentially?
Yes, you can, except in order to turn it into the A star, in order to work with A star, you have to have a heuristic function. So, as you said, you can always make the heuristic function a zero and see what happens. And then you can also make the heuristic function exactly the length of the actual shortest path and see what happens. So I would strongly recommend doing that as an exercise. And if you guys are interested, I can do the same thing and I can give you the solution to the A star algorithm based on those two assumptions. Yes, please. Second that. Okay. So we have a motion, we have a second.
Aye.
Okay, so do you guys understand what I'm talking about? Okay, let me just make it very clear. So you want to use A star on the previous homework assignment, okay? Okay, so I was just going to say this is G, that same thing. But you want to have make it two cases, okay? So the first case is, H of VW, okay, for all VW in V. just turn it into 0. See what happens, okay? The second one is to say for all v, w in v, make the heuristic function the actual shortest path from vertex v to vertex w. Now, since in this case, we are not really concerned about any vertex other than the destination, so that means we can simplify this a little bit and just say that, h of v d, because we know vertex d is the destination, is in fact L of v. Okay, do you understand these two notations? One is to say that there's no actual information in the heuristic function whatsoever. Okay, if you ask me, so Tag, what do you think is the shortest is the length of the shortest path from v to w? I say 0. But what about this one here? 0. I'm just giving you no information whatsoever to guide your search. Okay. The second one is to give you perfect information. Okay, so this time you're asking the oracle and say, oh, what do you think is a good underestimate of, so underestimate is not exactly a good name because it is exact now, it's not less than, but it's still the same admissible property. So you're now asking, what is a good underestimate from a particular vertex to the destination? And I'm going to give you the exact length of the shortest path. Okay, so I'm giving you as much information as it is possible to guide your search through the graph. So compare between these two and see how they differ when you execute the A star algorithm. Yep.
When you have the oracle, I'll tell you exactly like the length, wouldn't that execute faster because as soon as you found
Yes.
a matching link,
Every step along the way.
just move on to the next.
Yep. Every step along the way, the most promising vertex in O is the one that you want. And then the h function of everybody else, excuse me, not the f, the h, but the f function of all the other vertices is guaranteed, the f value are guaranteed to be more than the vertex, the f value of the vertex that is actually on the path itself. So it will be a very short search process. Now, there's one more thing you need to do when you run A star algorithm. Who is the start vertex?
That's just A.
Yep, A is a good one to play with because all the other ones only has one single edge to the destination. A is the only one that bounces off something else. So I would use, so the start vertex should be vertex A, and then the destination vertex should be vertex D.
From B you can go two routes, the BCD or BD.
From B,
You can do BD.
because they're equal distance, right? You can go BD, which is already 3, but if you go BCD, it's also 3. That is correct. Yep.
Do we have an additional office hour on Monday, like we have before we meet here at 12:45?
Yes. So I'll be here like right before the exam. So I'll keep my usual office hour from 11. So it's slightly more than an hour, but that's fine. Somebody has to buy me lunch.
We should probably make sure when it's 12:45, right?
Hmm?
That's what it's on the ARC. website.
Correct. It is 12:45 to 2:45. Okay. So there's one more suggestion, is to use the graph in the practice exam as another example. So you can use this graph. Now this one is a little bit more complicated, but you can still use it. But then you have to choose, which one is your start vertex, and then come up with your heuristic function. But you can use A star algorithm on this one too. Is that okay? Cool. So we still got 15 minutes left. Yep. Oh, the homework. That's right. I forgot about that. Okay, so we'll do the homework. My tablet is probably at 1% charge now. 6%. Okay, we can start up now. All right, so. All right, so this is your homework assignment. And I'm waiting for my tablet to start up. Well, actually, I can do it without that. So let me go back to the share folder and make the solution here, basically. Okay. And we'll go ahead and rename the sheet first. And we'll call it okay. So the spreadsheet is now available. We need to track a few things. We need to track the set Q. We need to track which vertex we pick out of Q, which is V. We need to state what incoming vertex we're considering, which is vertex W. And then we have the L function for all of these things. So we have L of A. Oh, E prime, that's right. Okay, so we have the E prime as a set of solution edges. Then we have L of A, L of B, L of C, and finally L of D. There we go. Okay. So the initialization is Q should start with all the destination vertices. In this case, there's only one, which is D. E prime starts as an empty set. Only the destination vertex has an L value of 0 to begin with. Everybody else has infinity. So basically, row 2 is the start condition of the entire algorithm. Do you guys want me to zoom in a little bit? I think that may be a little bit. Is that okay? Yeah, I can zoom in a little bit. There are certain ones that I don't want to resize because E prime is going to be longer. All of the other ones, oh, okay. Let's see. Oh, I cannot control click to get rid of one selection. Ah, okay. Hmm? Sorry? Yeah, those two are single vertices, so I think they will fit just fine. Okay, there we go. Okay, so the first thing we need to do is to, there's no choice initially. We have to pick D, okay, because, that's the only element in here. And then we have to look at all the incoming edges into vertex D. So if we go back to the homework assignment, we have incoming vertices from all 3 other vertices, because you can see that there's a vertex from A to D, there's a vertex from B, an edge from B to D, and there's another edge from C to D. The ordering is not important. You can explore the incoming vertices in any particular order. That does not matter. But since I'm listing it this way, might as well start with A. Okay. So switching back to the algorithm here. So we're looking at A. And then switching back to the question, because we need to know what is the cost of the edge. So the edge AD has a cost of 10. So now the question is the new path, the path that I have just discovered, which is from A to D directly using an edge, is that length shorter than the current length that we know of from vertex A to a destination, which is infinity? The answer is yes. So we go into the conditional statement. And in the conditional statement, there are a few things we have to update, but all of those updates can be on the same row in the spreadsheet, so there's no need to differentiate between those particular updates. So we basically say, okay, L of A is going to be updated to 10. We have to add the edge from A to D into E prime. And we also have to remember to add A back to the set Q. Okay. Next one is vertex B. So we look at vertex B. The edge from vertex B to vertex D has a cost of 3. Okay, so we switch back to the spreadsheet, and then we ask, is 3 less than what it already has at this point? Yep, so we need to update. This becomes 3, and then we add, technically speaking, we have to remove all the edges from B to whatever vertex that is in E prime, but since there's none at this point, we just say that, okay, we're just going to add 1. So we're going to add the edge from B to D at this point. And we also have to remember to add B into the set of Q because its L value just got updated. The next one is C, and I believe the cost of the edge is 1. 1 is less than infinity is true, so we update, and then we add that edge here, AD, BD, and CD, and then we add C to the set over here. So that concludes the for each loop, which is the last step of the while loop. So we go back to the beginning of the while loop, and then we look at Q and go like, is it empty? Nope. So if it's not empty, you cannot just pick an element this time because there are three to consider. You have to pick the one that has the lowest L value as your new V. So out of these 3, C has the lowest L value of 1. So C is the one that you have to choose. So in this case, C is chosen, and then you have the other 2 remaining in the set. So now the question is, are there vertices, that goes, okay, are there incoming edges into C from other vertices? And I really cannot remember, so we'll just look it up. Oh, B does, okay, and the cost of the edge is 2, okay. So this part cannot be reflected in the spreadsheet. Basically, we are asking, okay, so this part we still can do it, okay, so we have to put a B here, but there's no update, because when you look at L of C, it is 1. When you look at the distance of the edge from B to C is 2. 2 plus 1 is 3. 3 is less than 3 is not true. So we do not execute the then portion for this particular vertex. And there's nothing to add back to the set Q because B is not considered in this case. Okay, and that's the only vertex going from B going into vertex C. So we're done with vertex C. So now we go back to the while loop, the beginning of the while loop. We have 2 additional vertices left in Q. So we have to pick the one that has the least value. L of B has the smaller L value, so we have to pick B out of Q, and then we remove it from the set Q. So B is going to be chosen this time, and the set Q only has A left. So now we have to say, okay, which vertex goes to vertex B directly through an edge? So we are looking at something B, so there's AB. Oh, okay, cool. And let's see, we have AB, and that's the only edge, going from A to B with a cost of 1. Oops. Go back to here. So we say there's an incoming edge or incoming neighbor of A. And now we have to ask the question, are we discovering a shorter path from vertex A to the destination, to a destination? Yes. Yes, because L of B is 3, and the edge from A to B only has a distance of 1. 1 plus 3 is 4, and 4 is less than 10. Okay, so we got to update now. So this is now updated to 4, and then so this is the important update to E prime because you have to remove AD here. So there's no AD anymore, there's just AB left. Okay. Okay. And over here, there's no change, but you still have to state that, Sorry?
I don't think I wrote it down there because
Oh.
adding to it.
Okay, but I'm putting it there because the set, technically speaking, is updated. It just updated with the same value. Yep. Okay, but that concludes the for each loop because there's only one incoming edge to B from A. And then in the last iteration, there's only one vertex left in Q. So A is now here. So now we have to ask the question, do we have any incoming edges to A? And the answer is no. So that means that once we remove A from the set Q, there's nothing to do. You go back to the beginning of the loop. Q is now empty. You're all done. So if you want to, this part is not required, okay? But if you want to, you can state that G prime, which is the solution graph, is a two-tuple, where the first tuple is all the vertices, and then the second tuple is E prime itself. So E prime is just AB as an edge, BD as an edge, and then CD as an edge. And that's the entire thing. So are there any questions about the trace of this algorithm? Okay. So that still leaves us with 5 minutes. Yes.
So when I was doing this, I got the correct E prime, but when I was going through and picking out like picking out vertices from Q,
Uh-huh.
I was originally looking at like the lowest value. I
Ah.
still got the same E prime, but I wasn't looking at the lowest value.
Okay. So okay.
What
So
does that affect like the ending result?
that's a good question. So let me go back to the algorithm, and then we'll point to that line and ask the question. Okay. So the question basically is, if we look at Dijkstra's algorithm, and in this particular step, what if we do not choose the vertex that has the least value? Would it change the correctness of the solution? That's the first question. So what do you guys think?
Sounds like it does, really.
I'm not choosing the most promising vertex to
It
expand.
takes longer to do it.
Right. It will still be able to find the shortest path. Okay, but why? Because in your experience, it found the same. It came to the same conclusion. It basically, quote unquote, fixed itself, right? So now the question is, why is it fixing itself? If you choose something that's longer than it needs to be, how come it will still be able to fix itself? Yep.
I think it's because like every time you do it, you update Q again, over and over again every time you're doing it. So eventually you'll get to the shortest one because Q's updating each time you do it.
Yep. Because Q is a set. So even if you start with the most unpromising vertex and go backwards, you will still go back to the most promising vertex. So that is why it will still be able to find the shortest path, because the most promising, the correct vertex is still in the set. So you cannot avoid evaluating it. But when you evaluate it, it will meet the requirement of the conditional statement and it will update the edge. So as an exercise, okay, as an exercise, you can basically ask yourself and answer this question and go like, if we do not select the most promising vertex, okay, we change this line here and just say we randomly select a vertex in Q, how do we prove that it will still find the shortest path? And I would suggest use proof by contradiction. In other words, it finds a path, but it is not the shortest. And then show me how it is not possible not to find the shortest path. So that's an exercise, okay? You can kind of go through and try to figure that out. Yep.
Interesting that it eliminates the path from B to C, and doesn't include that in the algorithm. Because if you do like visually, A B C D, it would still be the same path as A B D. But
A, B, D. So there are two paths of three, cost of three, right?
so you do have two starts if you want.
Correct. So there are two. Okay, so that part has to do with. Okay, not this one. Okay, so that part has to do with the sequence of how we explore A, B, and C. So if you explore C before B, that will That won't change it though. Okay, so let's look at this step here and reverse these two steps. Because if you reverse these two steps, it doesn't change the L values. So that it still won't change the fact that we are still going to go for um, this particular solution. Yep. The reason it has to do with um, this takes 2 hops. This only takes 1 hop. So it always, this is the actual destination, right? So because we explore, okay, A doesn't really matter in this case, but because we explore every single incoming edge to the destination first, it is going to explore this edge before it has a chance to figure out that, oh, going from B to C then to D has the same cost. So that's why it won't change it. Now, one thing that you can also change to the algorithm to see how you can figure out, oh, there's a shorter path to do everything, is to change that one to a 1. Instead of a 2, make it a 1. Then it will go like, okay, in the first attempt, it will say B to D is the shortest path, but then it will figure out that B, C, D is actually going to be shorter. Then it will remove this from E prime and then use this edge instead. So I would suggest playing with the algorithm by changing just this distance from 2 to 1 and then see how the trace is going to be different. Yep.
Which will also have the same effect if you increase the 3 to 4.
Yep. Because what's going to happen is it won't change anything here except this is going to be this is still going to be a 3, this is still going to be a 1, but in this step here, it's going to update. Because BC, okay, because BC is 1, so that means in this particular step, this is going to be updated to a 2, right? It will update E prime, and it will also add B back into the set itself. But when in the next step, we are not going to choose. Okay, so that's going to update, how B is going to get to D, but it's not going to update how A is going to go in through B because that part does not change. So the only change you should observe is this row. Row 8 of the spreadsheet is the only row that you would observe an actual change. Everything else would change a little bit because the set and also the values have changed. But the biggest change is going to be on row 8 because the conditional statement is going to execute instead of being skipped. Is that okay? So there are all of these kind of hypothetical variations of questions that I have already kind of explored. So kind of think on those things for a little bit, because I think that's going to help. Because what I'm doing is I'm showing you how I think to come up with new questions. Yep.
Do you know we're going to review, we're going to study calculus?
We are not, well, that's a good question. I do want to go over predicate calculus, or at least show you what we can play with Prolog. So instead of formally introducing predicate calculus, we can just play with Prolog, okay? And my favorite is to use Jedi, Sith, and Star Wars stuff to talk about it. You guys, some of you might have read the notes on it and already kind of go like, okay, that's kind of interesting. So we can explore Prolog if there are no questions about the final exam. But the idea is for you guys to start to study for the final exam. And the other thing is I can also show you the solution of applying A star on the graph in the homework assignment, but using the 2 different heuristic functions. One is fully informed and one is not informed at all, and then we'll look at how the trace is going to look different. So you like that, huh? Okay, we'll do that on Wednesday. Cool.